Hello viewers, greetings to all of you. You are watching PMLS videos and this is Professor A.K. Pathak talking to you. As displayed on the screen, in this video we are going to talk about adherent points, limit points and isolated points of a set in a metric space. Some authors call adherent points as cluster points. Some call them limit points. Similarly, for limit points, the terms accumulation points or cluster points are also in vogue. So be careful, and before going through any comment or proof in any mathematical texts using these terms, please always see the definition of the terms in the text of your study. However, we are going to use the terminology shown on the screen. The space is also important. Our study is for metric space. If you are studying topological space, these concepts may deviate. But as far as the real line is concerned, we all know that it is a metric space with respect to the standard metric. So whatever we are going to study here is applicable on the real line. The topics being covered here require thorough discussion. So, to keep the duration of video shorter, we are going to upload videos in more than 2 parts. This is the first part in which we introduce the concept, formulate a definition, and illustrate the concepts with one simple example. We take the pair ED as a metric space and F as a subset of E. For the sake of brevity, we are also taking F to be non-empty. Our study is going to be heavily based on the concept of open spheres. Some authors use open sets or neighborhoods to explain these concepts, but we stick to open spheres. You know that open spheres are denoted by SR alpha, where R is the radius and alpha is the center. It is in fact a set of all those points of E whose distance from alpha with respect to the metric D is strictly smaller than the radius R. However, we know that every open sphere is an open set as well as a neighborhood of its points. Also, every open set or neighborhood contains an open sphere centered at its points. So these two statements jointly reveal that our study is equally good if we use open sets or neighborhoods in lieu of open spheres. So let us begin our study of adherent points, limit points and isolated points of a subset F in a metric space E. We are starting our discussion with the help of the concepts of interior points, boundary points and exterior points, which exist corresponding to any given set F in a metric space. Those viewers who are not aware of these concepts may watch the relevant video on this channel. Coming back to our discussion, we recall that all the points of E can be classified into 3 mutually disjoint classes separately consisting of interior points, boundary points and exterior points of the given set F. Further, we observe that an interior point is always a member of the set. Boundary points may or may not be a member of the set, whereas an exterior point is never present in the set. Hence, it is obvious that as regards to study properties of a set in a metric space, interior and boundary points of that set are more relevant. So, it would be a wise step to club them together and give a common name to them. We call them adherent points of F. But introducing a new term is not of much use in mathematics unless we associate a mathematical statement to it. So the question is, how to frame a mathematical statement for adherent points? A proper way could be to do away with the class of exterior points from the three classes and focus on the classes of interior points and boundary points. For accomplishing this job, let us have a look on the condition which is fulfilled by exterior points. What we are saying is alpha is an exterior point of F if there exists an open sphere SR alpha which does not contain any point of F. And in symbol, we are writing that there exists R greater than 0 such that SR alpha intersection F is equal to phi. Now, in order to exclude exterior points, we shall have to formulate a statement which negates this statement. What we are saying is that for alpha to become an exterior point, we need at least one open sphere with center at alpha which does not contain any point of F. When will it be not possible? Obviously, when every open sphere centered at alpha contains some point of F. Hence, the statement of negation is every open sphere SR alpha contains some point or points of F. In symbols too, you can see that the statement there exists R greater than 0 such that the intersection of SR alpha and F is empty is negated by the statement that for all R greater than 0, that is for all open spheres SR alpha, the intersection of SR alpha and F is non-empty. So this statement, which negates the condition fulfilled by exterior points, is good enough to be accepted as a definition of adherent points of F. Let us write it properly. A formal definition of adherent point is now on your screen, which reads as a point alpha in the metric space E is called an adherent point of F if every open sphere centered at alpha contains at least one point of F. That is, for all R greater than 0, SR alpha intersection F is non-empty. Now we know that all the interior and boundary points are adherent points, and therefore it is essential that we search for any special situation which may arise in the metric space. So we now try to inspect the situation more closely. So we are considering adherent points, and for adherent points we know that for all R greater than 0, SR alpha intersection F is not equal to phi, that is the intersection is non-empty. So let us take one SR alpha. So let us take SR alpha such that SR alpha intersection F is non-empty. Now we are considering two cases. The first case is when alpha is in F. If alpha is in F, then there is one possibility that this intersection consists only of the singleton containing alpha. The second case could be that this intersection of SR alpha and F contains some other points which we can call as P, which are not equal to alpha. Of course, these points P belong to the intersection, and therefore they belong to SR alpha as well as to F. The second case which we consider when alpha is not in F. Now if alpha is not in F, then there will be a third situation when SR alpha intersection F will be equal to only points containing P where P not equal to alpha. We are just taking a symbol P for those points which are not equal to alpha and which belong to SR alpha and F as well. So if we combine these two cases, then we can say that SR alpha contains at least one point P of F such that P is not equal to alpha. So there are two situations. One, when this intersection contains only the singleton alpha, and the second situation is when SR alpha contains at least one point P of F such that P is not equal to alpha. Now suppose that this is true for every SR alpha. If it happens, then what is the graphic? Let us see. If it happens, then suppose this is the set F and you are having a point alpha. You are taking any open sphere, you have one point. Then again you shrink the radius, you have another point, and you go on doing that. And since the points are so accumulated around alpha that you draw any open sphere centered at alpha, you are going to include one point of F different from alpha in the intersection. So here you can see that it is a case of accumulation or clustering around alpha. Now let us see this situation graphically. In this situation, you have this set F and you are having point alpha. Then your SR alpha intersection F is just the point alpha. The other points of F may lie somewhere here. So this is the case. It is the case when alpha can be isolated from another points of F. So these are two situations. You can visualize these situations like suppose you are going to attend a dinner, and in dinner you see that there is a very famous person having dinner with you. Then you will always see that person surrounded with some people. You won't be able to isolate that person. But if there is someone who is not that much known figure, then that person can stand alone in a corner and take his or her dinner. So that is the case of isolation. So these are the cases here also. In this situation, we call alpha is called an accumulation point or cluster point, or what we are going to say it, limit point. Now the rationale behind calling it a limit point will be revealed in the second part of this video, when we will show that it is in fact a limit of some sequence of the points of f. And the second situation in which alpha can be isolated, we say that alpha is an isolated point of f. So one thing is very clear, that for limit point you are using universal quantifier. You are saying that for every SR alpha this should happen. For every SR alpha this should happen. And in the case of isolation point, you need one open sphere SR alpha which isolates alpha from other points of the set F. Therefore, if in symbol we want to write it, then for isolated point, in symbols we can say that their edges are greater than 0 such that SR alpha intersection F is the singleton containing alpha. And in the second case, when we are considering the limit point, then we are using universal quantifier. In that case, we say that for all r greater than 0, that is for every open sphere, this intersection is containing some point other than alpha. It means it is not equal to the singleton alpha. Also, it is not equal to phi. So SR alpha intersection F not equal to phi. This we have already taken. So combining these two, you can write that SR alpha intersection F difference this singleton is not equal to phi. So for limit point, we can have this symbolic representation. What we see that adherent points are classified into two types. One, isolated points, and the other is limit point. For isolated point, there exists an open sphere SR alpha such that SR alpha intersection F is the singleton containing alpha. Whereas for the limit point, we say that open sphere SR alpha contains some point P of F with P not equal to alpha. One thing is also clear, that these isolated points are always members of this set. You can see that this situation can happen only if alpha belongs to F. So isolated points are always members of this set which we are considering, but limit points may or may not belong to the set. Alpha belongs to F or alpha does not belong to F. Anything can happen. So It was a brief attempt to provide a conceptual idea of adherent points, limit points, and isolated points of a given subset F in a metric space E. However, before I proceed to the next slide, let me put two cautions, which probably have been put before you earlier on this slide. While showing these diagrams, we have shown SR alpha as a subset of F. However, it is not necessarily the case. SR alpha may not be a subset of F. The only thing is that its intersection with F is non-empty. The second caution is, while discussing limit points through diagram, we have considered the case when alpha is a member of F, that is necessarily an interior point of F. However, you may take alpha on the boundary of F, that is alpha as a boundary point of F, and still visualize the same situation. I hope now you are able to understand the concepts of these points, and therefore we proceed further. We now recapitulate what we have studied. As far as adherent point is concerned, we are saying that a point alpha in E is called an adherent point of F if every open sphere centered at alpha contains at least one point of F. That is, for all r greater than 0, SR alpha intersection F is not equal to phi, means it is not empty. The limit point is defined by a point alpha in E is called a limit point of F if every open sphere centered at alpha contains at least one point P of F with P not equal to alpha. Equivalently, we can say that for all r greater than 0, the intersection of SR alpha and F, difference the singleton containing alpha, is non-empty. And lastly, the isolated point is defined by a point alpha in E is called an isolated point of F if there exists an open sphere SR alpha with SR alpha intersection F equals the singleton containing alpha. We have also observed that adherent points and limit points of a given subset in a metric space may or may not belong to that subset. However, the isolated points will always belong to the set. So we have studied so far the definitions of adherent points, limit points, and isolated points for a given subset F in a metric space E. Lastly, we are proceeding to see a simple example to illustrate these concepts. So here we are considering the metric space Rd, and the set F is the union of semi-closed interval with endpoints 0, 1 and the singleton containing 3. And we are going to investigate for the limit points and isolated points of the set F in the metric space R. We are also putting for reference the conditions which are obeyed by the points of metric space for being a limit point or isolated point. Now in RD, we know that any open sphere SR alpha is nothing but an open interval with endpoints alpha minus R and alpha plus R. Now let us see this picture. On this picture, the points of the set F are shown on the blue strip just for convenience. And now we are going to investigate. As we know that exterior points are not to be considered, therefore the points of the real line which are not on the blue strip are not of our interest. So we are considering the points 0, 1, 3 and also all the points between 0 and 1. Let us see the boundary and interior points. So we have already written that the boundary points are 0, 1 and 3, and all the interior points are forming the set open interval 0, 1. So before we proceed to investigate the limit points and isolated points, one observation is very clear, that 0 is a boundary point, but 0 is not in the set. What does it mean? 0 is a boundary point. I am writing 0 is a boundary point, but 0 does not belong to F. So 0 is an adherent point, but it cannot be an isolated point. So 0 cannot be an isolated point. Why? Because we know that all the isolated points are members of the set. So 0 being a boundary point is an adherent point, but is not an isolated point. So obviously 0 is a limit point of the set F. The other way to look at it directly through the definition of limit point, that if you put any open sphere around 0, what will be the open sphere around 0? So open sphere around 0, if I put SR 0, then this is nothing but the open interval minus RR. So if I take any open interval around 0 and call it minus RR, then you can see that this open interval includes some points of F which are different from 0. And therefore, I can very easily write that minus R intersection F difference the singleton containing 0 is not equal to phi. So even by the definition, what we see that this is happening for all r greater than 0, and therefore 0 is a limit point of F. So this was a quick observation, and this is by way of using the definition directly. Similarly, if you look at any other point in between 0 and 1, let us see. Suppose this is point alpha in between 0 and 1. Then any open interval with center at alpha, SR alpha, is of the type alpha minus R, alpha plus R. You take any open sphere around alpha. Again you will see that there are some points of F which are different from alpha, and therefore I can write that for all r greater than 0, the intersection of this open interval with F difference the singleton containing alpha is not equal to phi, because that open interval, whatever interval you take with center at alpha, is going to contain points from F which are different from alpha. And therefore, if you take alpha in between 0 and 1 is a limit point. So all the points which lie in the open interval 0, 1 are limit points. Similarly, if you see for the point 1, then SR1 is nothing but 1 minus r, 1 plus r. This is the open interval. And you take any open interval around 1. Again, there will be some point of f which are different from 1. And therefore, for all r greater than 0, you can write that 1 minus r, 1 plus r, intersection f, difference the singleton containing 1 is not equal to phi, and therefore 1 is also a limit point. But now see the case of 3. Here for 3, you can see that you can have an open sphere with endpoints 2 and 4. And this open sphere is nothing but S1, 3 you can say. Then this is with endpoints 3 minus 1, 3 plus 1, which is nothing but 2, 4. So with this, if you take intersection of f, then you are having just one single point, and that is the point 3 itself. And therefore you see that 3 is an isolated point of f. Practically, the better way is, if you are given a point in the set to inspect whether it is a limit point or isolated point, try to first isolate it through an open sphere in the metric space. If you are able to isolate it, then it is an isolated point. Otherwise, it is a limit point. So what should be the correct course of action? First, if you are given a set in the metric space, then only concentrate on the interior and boundary points. Those points are adherent points, and they are the limit points or isolated points. Don't think about the exterior points. Now, after having considered the interior and boundary points, the points which may not be in the set are boundary points. But boundary points, if not present in the set, are certainly limit points. But boundary points present in the set may or may not be limit points. Similarly, interior points may or may not be limit points. They can be isolated points, they can be limit points. So this is the whole scenario if you are investigating for limit points or isolated points of a given subset in a metric space. In the next part, we are going to deal with many more properties of these points. Till then, goodbye. Thank you.